This video covers torque. Now we've seen torque before. It's represented by a tau. It is the tendency of a force to rotate an object about an axis. Now, torque is a cross product of R cross F. Now, R is a lever arm, and it is the distance from the pivot point to the location where the force acts. Now, we've seen a dot product before, where work is the dot product of R and F, and we said that these two components needed to be parallel to each other, or wanted to be parallel to each other. This cross product tells us that R and F want to actually be perpendicular to each other. So R cross F translates to RF sine theta. Now, just like in work, it's going to be very important that you understand what angle you need to put into this particular theta. Torque is analogous to force. What that means is if you think back to Newton's second law, which is the sum of the forces is equal to mass times acceleration, this tells us that if we have an unbalanced force, we're going to have linear acceleration. Well, when we say a torque is analogous to force, that means if we have torques or unbalanced torques, we're actually going to have angular accelerations, but we'll see this again in a little bit. Now, the most important thing is going to be that force and R are perpendicular to each other. So in this example, we have a force being applied at an angle. Well, the component of force that is perpendicular to R would be F sine theta. So R times F sine theta will produce a torque. So these are three of the most common examples. If we have a force that's being applied like in this first situation, then the angle between R and F is 0. And we can see that the sine of 0 is 0. So there will be no torque produced or no rotation produced. The greatest torque is going to be provided when you have a force that is perpendicular to R. Again, when your theta is equal to 90, because the sine of 90 will be equal to 1. And so your equation reduces down to torque is equal to R times F. Now, if you have a force that is applied at an angle, then you can use theta as your angle, carefully, and torque is equal to RF sine theta. Now remember that torque is made up of R times F, and R is measured in meters, F is measured in newtons, so torque will be measured in Newton meters. Now, just like we saw in rotational kinematics, anything that is clockwise will be negative, anything that is counterclockwise will be positive. So if a force produces a counterclockwise rotation, then the torque produced is also positive. So here, what you're seeing are forces causing counterclockwise rotation, so positive torques. Here, you see our forces are causing clockwise rotation, so they produce negative torques. Now think about a circle with its axis of rotation in the center, and we are applying a force a distance r away from our axis of rotation. Now, if we look at this force, it's going to cause a clockwise rotation, or a negative torque. If we apply a force here, also a distance r from our axis of rotation, this is going to cause a counterclockwise torque, or a positive torque. Now, if these two forces are applied and this object does not rotate, what we're saying is that our sum of our torques is equal to 0. And this situation is known as static equilibrium. So if that's true, that means all of our positive torques plus all of our negative torques is equal to 0, or our counterclockwise torques are equal to the sum of our clockwise torques. What that means is if you look at this example, we have a 3 kilogram box 1 meter away from our axis of rotation, in this case our fulcrum, which is this triangle right here. It's our axis of rotation. And we have a 2 kilogram box some distance away from, again, our axis of rotation. Now, if we want this seesaw to be balanced, then the sum of the torques needs to be equal to 0, or the sum of the counterclockwise torques needs to be equal to the sum of the clockwise torques. In this case, on the left-hand side, the force that's causing rotation is going to be mass times gravity. And again, multiplied by a distance r away from our axis of rotation. On the right-hand side, our 2 kilogram mass will also experience a mass times gravity. Again, some distance r away from my axis of rotation. So again, if I want this entire system to be in equilibrium, then we need these two quantities to be equal to each other. Or to say that our 2 kilogram mass is 1.5 meters away from my axis of rotation. Now our last situation assumed that the plank that these two masses were sitting on was massless. But if that plank is not massless, meaning it does have mass, then we can actually calculate the center of mass of that plank. And if it's a uniform mass, then the center of mass will be located right in the middle at a distance L divided by 2. That means if we still want our whole system to be in equilibrium, that means causing no rotation, we need to take into account the force that's going to be acting on the center of mass, which is still mass times gravity, but now it has to be included. So down here at the bottom, we have the mass of one object times gravity times its distance away from the axis of rotation is going to be equal to the mass times gravity of my second object, plus the mass times gravity acting on the center of mass. Now for these situations, you just need to make sure that you read whether or not whether the plank that these two objects are sitting on is going to be considered massless or not.